I don't think I am, John. Thank you, though. Good morning, everybody, and welcome to Ellensburg, Washington, USA, home of Central Washington University. Thank you for joining us today. This is a live stream, and you can see the title slide in front of you. How to build a super eruption. Oh, she changed the title again. God dang it. All right. Nice. Ayla Pamukcu is with us from Stanford University, and we are very excited that she is here. Looks like we're 5 by 5. I'm so pleased to see that. Thank you. I'm going to get rid of the title slide, but I guess before I do that, if you're watching this in replay, the lecture will begin in about 15 minutes from now. You can skip ahead 15 minutes to the beginning of Ayla's program, her lecture. But those that are watching live, and we have approaching 100 live viewers starting to pour in, let's visit with some of you and get a sense of this. There's a nice energy in the room, for sure. There's your first look at Ayla, and you know Hannah Shamlu. Very exciting times here. Hi, everybody. Welcome to Discovery Hall. This is the home of the geology department here at Central Washington University, and we have a special guest from the Spirit Lake Pluton Project, Ayla Pamukcu. Where are you viewing from today? Can I say hi to a number of you before we turn the camera around? We've got some townies here filtering in, as well as our old standby students. Springfield, Oregon, North Central Washington, Long Valley Caldera, Webb Lake, Wisconsin, Tumwater, Washington, Burlington, Washington. No free beer here, Jeff. It's Friday morning. Falls City, Washington, that's Kevin. Boone, North Carolina, Petersburg, Alaska, LaPorte, Minnesota. Oh, especially loud this morning. I love it. This late in the spring quarter, one wonders if you'll have energy at all, but we've got energy galore here today. Massachusetts, Winter Gardens, California, Kirk from Philomath, Lebanon, Oregon, Boulder Creek, California, Grimsby, UK, North Vancouver, BC, French Riviera, hello, Laredo, Résine, hello. You're from France. That's French. Hot Orlando, Florida, Sierra Foothills, Los Angeles, Hamburg, Germany, Hillsdale, Michigan, Aamodt, Norway. Hello, Nina. Somebody's in Ellensburg, Washington. Hello. Sharon's in the Malaga Slide. Hi, Sharon. And so on. Thank you so much for being with us today. Before I turn the camera around, I guess you'll hear this in a few minutes, but we only have one more talk. I'll save that. But you can make a note if you like to come visit us in person next Friday for the last spring talk of the school year. Michael Eddy from Purdue University will be here. Friday, May 16th, noon Pacific, in room 103 of Discovery Hall. You are welcome to come visit with us and visit Vindman's and the whole thing. Okay, we'll start the program in 10 minutes or so. I'll turn you around and give you a sense of the room. In fact, the shadow zone is mostly packed, and the part of the room that you're going to see is mostly empty. I don't wonder what that's about. People don't want to be on camera, I guess, today. All right. One more thing, James Gennaro IV is the president of the Geology Club, and there's some brand new Geology Club swag, brand new t-shirts by James and the club. You gotta love it.
hot?
Oh, I'm hot.
Oh, I'm hot all right. Yeah, most of my customers seems like just about for some.
Hi. It's been a while.
It has.
How are you?
I've been doing all right.
Good?
Just finishing all my biology stuff because double major life.
That's a lot.
Yeah. But I'll be done next spring.
Oh, you got another full year.
It's because I had to do a language, otherwise it'd only be a quarter.
Oh, my.
Or just do a language because otherwise it'd be a quarter.
Wow.
Yeah. Which sucks, but hey,
That does
what
suck.
can you do?
Did you know that a couple years ago?
We thought that transferring over my high school transcript wouldn't have been as disastrous as it was because there's a bunch of college credits on there that are not good. So we did a test transfer and it ended up dropping my GPA to like a 1.8.
Really?
Yeah.
Because you did running start type stuff?
Yeah.
What is the purpose of running start if it actually?
Well, it was because I did really bad.
I see.
Yeah, it was because I was not ready to have that amount of responsibility
I
over
see.
my education.
Okay, well that's well, thank you for that
Yeah.
honesty. Like that's part of it. But even if you're totally on top of your game, it feels like sometimes it's not
Usually-
counting or there's a huge gap
Usually
between.
you end up ending running start with a transfer associates.
Yeah, okay.
So yeah,
Okay.
it's made to like get you within like a community college level associates
Right.
by the end of high school.
By the end of high school. So
Yeah.
from my point of view, then
Why don't you just be in college? Yeah.
yeah. All right. Well,
Yeah.
seems like you've processed it mentally and you're
I got over it a long time ago.
okay. All right. I'm not going to stir up all those feelings again then. Yeah.
They need to write that through. I was just going to see if you guys want to do like an invitation stay sometime. And I can open up for you.
Thank you.
It'd
Yeah,
be
it's,
close. It'd be easy. Wildflowers are just starting. So next month, 2 months, it's pretty nice up there.
thank you for your kindness. I'll run it by her. I'm guessing she's trying to keep a low profile, but maybe she'd be up for it. I'll pass it along to her. Thank you. Very nice of you, Steve. Thanks. Yeah. Yeah, we're
Wes is doing good. He's probably watching right now.
Okay.
So that's why I even go like that.
Hi, Wes.
Wave at him.
Oh yeah, hi Wes. Wes Engstrom. Wes, thanks for watching. There's your friend Steve. Thanks, Steve. Thank you, Steve. Hey, how are you going?
Pretty good. Hi there.
Doing. Hello, nice to see you.
Nice to see you too.
Hey. Hi. Have we met?
No, we have not. We just drove from Boston.
You
here.
did?
Yeah. Because it just so happened I had a day off of work. My husband was available. We could make the drive over here.
Oh, good.
Yeah.
Oh,
Yeah.
welcome. I'm glad you found the
Oh,
place.
yeah. It was right there, so it was
Okay.
very easy. It
Nice.
feels good to be here, though.
Good.
Yeah. I almost want to go back to school.
Well, almost.
Yeah.
Yeah. Well, thank you. Yeah,
Yeah.
we work hard to create a certain environment here, and
Yeah,
It's
it's
happening,
Great. I mean,
yeah.
I've been following this, and it's funny because my brother, who lives in St. Louis, is the one who got me to tell me about you.
okay.
And he has not been able to come up here for a while. 'Cause
I
I
see.
actually started in geology also.
You did.
I did. And
Well, you should come back then.
yes,
What the
I
heck?
know. I want to. I really do.
Okay.
I mean, that's the one thing unfinished in my life that I'd really like to complete.
Okay.
But have to figure out how to do that.
That's right.
Because
Well,
I'm ready and willing.
good. What was your name again?
Doris.
Doris. Well, it's really nice to meet you.
Nice to meet you too.
Well, good. Well, I hope
I'm
you.
glad we made it. Oh,
Me
there's
too.
My husband Gary.
There's your husband. Yeah, hello.
So did she get her selfie with you yet?
Not yet. We'll do that afterwards. How about?
'cause I
Yeah,
have to
we're
send it to my
She
brother.
found out
Okay.
about you through her brother.
okay. We can do that.
Yeah.
Totally.
I'm Gary.
Gary, it's nice to meet you. Yet another Gary. Okay. We got, how many Garys do we have by now?
Gary is
You're-
always the troublemaker.
You're Gary from Bothell.
Yes.
Okay.
Yep.
Wow.
Yeah, we're really looking forward to this one. I actually watched your last interview with Ayla
In
With
your bare
Ayla?
feet.
last night, just to kind of refresh.
Good. Well, I'm excited for this
She
one too.
explains it all to me. So.
Okay. Well, good. I'm glad you found us, you guys. Nice to meet you too. Morning.
Hello there, Nick.
Hello, Roger.
How you doing?
I'm doing well.
Fine.
Thank you.
Looking good.
Thank you. You too. Yeah.
Do you have a sample of Mount St. Helens ash?
We do have quite a bunch of containers of it.
Oh, okay.
We do. You got more for us? Well,
You don't need any more.
I guess I don't, but I'd love to. We could always use a little more if you wanted to pass it along. Either way.
I do nothing but sitting
Okay.
on my shelf at home.
Well, thank you. I'll share that with the people watching from home right
Put your
now.
finger in it.
I will. Yeah. Thank you.
I had to use the heavy-duty pliers to open that thing.
Okay. Okay. I'll share it right now. Thank you for the gift. I'll share with the viewers. Jordan Carey on the clock. A little 1980 Mount St. Helens ash. Okay, we're going to mic you up right now, Ayla. I see the laptop's going already. I need to decide if I'm going to be a jerk or not. Okay, I think however you want to, what you just had was great, and then I'm going to ask the viewers if they can hear you. All right, let's make some small talk for just a second. We'll hear if they can hear you.
Do you have any dogs?
No, next question,
Yeah.
please. Cats? Yes, we have one. You have children.
I do, yes.
How many and what are their ages?
2 ages, almost 4 and almost 6.
Nice.
Yeah.
Oh, that's really cool.
Yeah, they're a blast.
And their social security numbers, please.
Yeah, I wish I had that memorized.
Viewers, can you hear Ayla? Oh, they can. So they have a little code, 5 by
Fantastic.
5, loud and clear. Okay,
Fantastic.
good. And in addition to that, in just a second, I'm going to connect your mic to this little
Speakers.
speaker, so we'll just project you a little bit.
Sounds good.
Okay. And this is you?
That's
I
me.
think we're ready. Okay.
Okay.
We live? We good?
We're about ready to start, sister.
Now I'm hot.
Oh, Scion with a smirk. Scion with a smirk, texting with God knows who.
Oh, okay.
Well, hey, everybody.
That's great. That's great.
What a nice crowd. What a nice full room. People are walking by an open auditorium, not sure if they want to hang out. They hear that there's a party going on in here, but they kept walking. All right. Very good. Thank you. Thank you. Can you hear me through this speaker okay? Oscar, thank you for the head nod. Oscar, how did the teaching go this week in this room? Double thumbs up and double high five as well? It doesn't get better than that, Oscar. Thank you for pitching in. I'd like to make a few quick announcements, and then Hannah Shamloo will do the introduction of our speaker today, and then we're off and running. Most of you have been to many of these talks, so you know the format. We'll do some live Q&A at the end. We have many visitors from out of town because they know of our speaker today, and they wanted to get a chance to meet Ayla in person, so that will be happening after the talk. But my job is to tell you about one more talk this spring. Just one more. So, we had 5 speakers set for this spring. Our first canceled because of some restrictions. They were not able to travel from Spokane. That's why we canceled that one. And Sarah from British Columbia was going to be coming on May 30th to finish out our series. But she has concerns about getting across the border and getting back. So, that's not happening either. We are going to do a recorded Zoom interview. Hannah and I will be interviewing Sarah in late May. So if you are very much looking forward to learning from her, that's our plan B for Sarah from BC. So that means, in addition to today's talk, we just have one more, and that is Mike Eddy from Purdue University will be here next Friday. And Mike and Ayla are working together on a new project involving the Spirit Lake Pluton. And so there's field work happening this weekend and all through next week with both Ayla and Mike. So we're catching Ayla at the beginning of their stay with field work, and we're going to catch Mike Eddy right before he heads back to the Midwest from Purdue. So we're really excited to have both of these fine scholars, researchers, and teachers with us today. I think that's the end of what I wanted to say. Hannah, do you need to announce anything for your course or anything related to that? You've got everybody? Yeah, got everyone. Okay, so we're going to hear a little intro from Hannah, and then Ayla will be ready for you. Thank you.
All right. Hi, everyone. It is my great pleasure to introduce Dr. Ayla Pamukcu, my well-respected colleague. She is a volcanic petrologist and geochemist, and she's originally from the Philadelphia area, and she had a long, amazing journey all the way to Stanford, where she is today. So she originally did her Bachelor's of Science in geophysical science and a minor in Near Eastern Science at the University of Chicago in Illinois. She did a master's and a PhD at Vanderbilt University, and then did 2 postdoctoral fellowships, one at Princeton and joint with Brown University, and another at Woods Hole Oceanographic Institute. Very impressive. And then at 2019, she joined the faculty at Stanford University in the Earth and Planetary Sciences department. So we're very excited to hear from Ayla today, so please help me welcome Dr. Ayla Pamukcu.
Thank you, and thank you, Hannah and Nick, and all of you for coming. It's a real pleasure for me to be here today to talk about something on screen. There it is. Okay. One of my favorite topics of all time, which is super eruptions. And here you can see an image of the Long Valley caldera from the Bishop Tuff super eruption that happened in California. So unlike your typical cone volcano, they make nice big holes in the ground. So we'll talk about these really enormous eruptions today. But before we get into that, I thought I'd introduce myself a little bit. So like Hannah said, I'm a volcanic petrologist, which means I study the products of volcanic eruptions to understand magmatic processes and conditions prior to and during a volcanic eruption. And so I mostly study the stuff that's coming out of those volcanoes, but to the extent that the magmas that don't erupt tell us something about the magmas that do erupt, I'm also involved in studying plutons, like here at Yosemite. Now, there are a whole ton of questions that one can ask about volcanic systems, and these are kind of the range of questions that I have been looking at. So things about storage and geometry of magma bodies. Where do magma sit in the crust, and what shape are they? This would have some implications for how we actually look in Earth's crust and try and find magmatic systems that might erupt. The other is timescale. So how long do eruptible magmas sit in the crust, and when and how fast do they actually erupt? And then finally, these questions about the generation of magmas. How are magmas generated, and how do eruptions start and stop? Now, volcanic eruptions create these really fantastic images, right? Where many of us are probably used to seeing these really evocative volcanic eruptions that have been happening. We've been very lucky in the last several years that there have been many exciting volcanic eruptions going on globally. But whenever we see these sorts of images, we also see the images of death, destruction, and disruption that these kinds of volcanic eruptions can have. And whenever I see these images, I'm pretty amazed because of just how incredibly dinky the volcanic eruptions are that are causing them. So most of the eruptions that we are used to seeing, if we look at this volume of magma that's being erupted, are less than a cubic kilometer of magma actually coming out. And, but we know from the geologic record that volcanic eruptions can get to much larger sizes, orders of magnitude larger. And it's these eruptions, or super eruptions, that I'm focusing on today. So these involve hundreds to thousands of cubic kilometers of magma, specifically silicic magma. So what I mean by that is if we look at this total alkalis versus silica diagram, we're sitting up here on the high silica end looking at rhyolites, trachytes, and dacites, and their intrusive compositional counterparts, granites, cyanites, and granodiorites. And given this very high silica content, it makes these magmas incredibly viscous, and so they produce extremely explosive and violent eruptions. And they're very short-lived. They're on the orders of days to a year. So these are different from things like continental flood basalts, which create hundreds of thousands of cubic kilometers of magma, but they're being erupted over hundreds of thousands to millions of years. So these are geologically instantaneous events. Interestingly, none of these have occurred in recorded human history, but that doesn't mean that one can't occur in the future. And given the potential, the havoc that these tiny eruptions cause, we can only imagine what these big super eruptions might do to the world. And these are just some artists' renditions of what a super eruption might look like. Again, we haven't seen a super eruption, so we don't really know what would happen, but it could be pretty intense. And what that means is that it's really important for us to study deposits from past super eruptions to understand when, where, why, and how a future super eruption might happen. And so that's kind of the realm that I work in. And there are lots of different scales that you can take when you look at these eruptions, or any volcanic eruption. You can go from the field to the hand sample to the crystal, and even smaller than that. And there are so many different aspects on each one of these levels that you can study. And so what I spend a lot of time doing is taking methods that fit within each of these categories and trying to put them together to understand from a variety of different scales and a variety of different pieces of information what's happening in these magmatic systems. So to sort of put together what it is that I and my students and my group do is we integrate data from different scales and perspectives to understand the generation, storage, evolution, and eruption of magmas. As a function of this, we're also involved in the development of new and better methods to address these questions, and I'll show you some of them today, but they have applications that range well outside of volcanic petrology, so hopefully you'll see something that might actually be useful to you. And then, although I'm specifically talking about super eruptions and silicic magmas today, other people in my group are spending time employing this approach to look at other kinds of magmas, so whether they are smaller volume eruptions that are also silicic, or other kinds of eruptions that are less evolved, more basaltic, different environments that they're happening in. So we're really taking this approach and expanding it very broadly. Today, the information that I'm going to be showing you is based on several different super eruptions that we've looked at around the world, 3 from the continental US and 3 from the North Island of New Zealand in what's called the Taupo volcanic zone. So just to give you a little bit of an introduction, here's the Bishop Tuff. That was that caldera that I showed you at the beginning. About 1,000 cubic kilometers of magma erupted, and you'll see here that it's compositionally very homogeneous, so about 75 to 77 weight% silica, not a lot of variation in the composition. Here in the back, you can see some of the airfall tuffs that came out in the early erupted portion of the volcanic sequence, and these are some of the welded ignimbrites from the late erupted portion. So had these 2 different phases, but overall about 1,000 cubic kilometers of very compositionally similar magma. This is in contrast to the Peach Spring Tuff, also about 1,000 cubic kilometers of magma. But what you see here is that there's quite a bit of variety in terms of the composition of the magmas that came out here, going from rhyolites, high silica rhyolites, and low silica rhyolites in the outflow to trachytic magmas within the caldera itself. And here you can see in the back in this cliff forming unit is the Peach Spring Tuff. In some ways similar to the Peach Spring Tuff, we have the Sunshine Peak Tuff, which was a bit smaller, about 350 cubic kilometers, but it also has this compositional variability from rhyolite to trachyte. What's also quite neat about it is that within the caldera and on the edge of it are these intrusive compositions that seem to be related to the things that came out. So this place gives us a really great opportunity to look at this question of what is the relationship between the magmas that erupt and the magmas that don't, the extrusive and the intrusive magmas. And then finally, we have these 3 volcanic eruptions out of the Taupo volcanic zone. 2 super eruptions and 1 not so super eruption, but has interesting qualities that enable us to look at this in some interesting relationships between really large volumes and smaller volumes. So we have the Urunui supereruption, which was the most recent supereruption in Earth's history, about 530 cubic kilometers, with a significant variability in terms of the rhyolite component there, the high silica component, but it goes from low silica to high silica rhyolite. We have the Oakuri Mamaku eruptions, which came out of 2 different calderas at the same time. 280 cubic kilometers of magma that show quite a diversity of compositions, but what's really quite interesting is that it was this paired super eruption out of 2 different sites at the same time. And then we have our not so super eruption, which is the Taupo super eruption. It's not super, it's 35 cubic kilometers, but it's still an extremely large eruption. And what's interesting about it is it's lower in silica content than Urunui, but it is very constrained in terms of its composition. But importantly, it comes out of the same exact caldera as the Urunui did. So it gives us a really neat opportunity to look at systems kind of taking out a little bit of the structural and tectonic differences that you might take from comparing one eruption to another eruption when it's coming out of the same volcanic center. So a really neat opportunity to compare these 2 different levels of size. Now, the main rock that I use to study these is pumice. And if you go on Wikipedia, you see that it has an awful lot of applications in the real world. But what they are missing is the most important and the best application, which is studying volcanoes. A critical piece of information. So if any of you is a Wikipedia editor, please go in and fix this problem. Because what is so amazing about a piece of pumice is that it's a little parcel of magma that's come out to the surface, and it captures moments in time in many different ways. And there are lots of different components of a piece of pumice that we can use. So pumice contains vesicles, which are little air pockets that we can use to understand the bubble population and the eruptive process itself of the magma. Most of a piece of pumice is comprised of this matrix material, which is actually a glass. It's melts that quenched when it hit the cold air. And so we can use the glass compositions and textures to understand something about the melt as it was erupting or just before it was erupting. We also have crystals, and these crystals, we can use their shapes, their sizes, their distributions, and their compositions to understand the evolution of magmas. And then still smaller within crystals themselves, we have these glass inclusions, these melt inclusions, and we can use the textures and compositions of those to understand the melt long before it erupted. So the crystals that capture them say those melts can tell us something different than this matrix melt. So lots of different pieces of information that are being held in a single piece of pumice, which is really, again, why it's so critically important. So those are the main tools that I use, and we'll talk some more about that. But if I had to kind of describe the questions that we have in a cartoon-like shape or cartoon-like image, we spend a lot of time looking at how deep these magmas sit in the crust, what shape they take, how they're generated, why they erupt, and how long they sit there before they erupt. And if I were to try and tell you about all of these questions today, it would take me much too much time, so I'm not going to do that. I'm going to mostly focus on how long they sit there and why they erupt. But I am going to give you the take-home points from the other pieces, so you, at the end, have this cohesive idea of how I think about building a supereruption, at least at this point. So first, looking at how deep we sit, the work that we've been doing really suggests that eruptible silicic melt bodies, these very crystal poor, melt-rich bodies, sit in the mid to upper crust, predominantly in the upper crust, and that melts that are extracted from a deeper system, a mushy system, can erupt directly from that depth, or they can have a sort of a piecemeal movement upwards and experience some residence at shallower depths. In terms of the shape that these magmas take, in some cases, it does look like they are comprised of single batches of magma that are zoned vertically in composition and temperature and crystal contents. But in other cases, we see evidence that they are comprised of multiple laterally or vertically juxtaposed magma bodies that simultaneously erupt. And then this question of how these magmas are generated. So we are seeing pretty commonly that ages and compositions of minerals in both intrusive and extrusive magmas suggest that they're genetically related. But there's no sort of one model that always describes it. So in some cases, we're finding that really large volume rhyolitic eruptions involve melts that have separated from crystals, that you leave a crystal residue behind, and that's what the pluton is. This is what's known as the mush model. But in other systems, we're finding that the volcanics are preceding the actual building of the pluton. And so that suggests that there's a different kind of genetic relationship between those. And this is something that we're exploring in some more detail right now, and is a major, both of these are major models that are being explored in the literature, generally speaking. All right, so now we're going to get into the meat of things, and I want to spend time talking about how long these magmas sit there in the crust. And for each of these, I hope you can see that I am not the only person involved here. There are tons and tons of collaborators, so I don't want to forget them by any stretch of the imagination. All right, so when we talk about this question of longevity, or the residence times of magmas, I want to focus on the fact that I'm looking at how long do these magma bodies persist in the crust in an eruptible state. What I mean by that is very melt-rich, crystal poor, movable. Once you get too many crystals, you can't actually move the melt, you can't actually erupt it. So I'm talking about the time when it's really melt-rich. But I also want to emphasize that there are some studies that suggest, many studies that suggest, that systems can kind of wax and wane. They can spend time in a very crystal-rich state in which they're not eruptible, and very crystal-poor states in which they are eruptible. Some suggest that they're perpetually in a warm state, we call it, versus going through this variation in cold and warm storage. Most of the techniques that I'm going to be talking about today only allow me to get at the last period of time in which this system was in a melt-rich state and eruptible. So most of what I'm looking at here is not if this system spent time in cold storage, not this entire history. So really just this last period. And in theory, that's the period that we care about if we think about how long is it going to be before this thing erupts. I want to know how long that last period is going to be. But this question has been debated for a very long time, with some studies suggesting that they sit around for extended periods of time, tens of thousands to millions of years, while other studies suggest that they sit around for very short periods of time, decades to millennia. And I think that the Bishop Tuff really represents this difference in terms of the timescales that people have retrieved. So you can see here that these are residence times that have been estimated for the Bishop Tuff magma body, or magma bodies, since 1989 to 2020. And you can see that they span everywhere from decades to millions of years. You can also see that many different methods have been applied to this problem. But ultimately, there's this discrepancy here that we need to better understand. And so I'm going to talk to you about 3 different ways in which I'm spending time getting information about time. Crystals are these incredible repositories of time. As they grow, as you spend time and the crystals grow, they grow in size through time. They develop compositional zoning, these tree ring-like features through time. radioactive nuclides in their structures undergo radioactive decay through time. And believe it or not, but these little melt pockets, these melt inclusions, actually change shape in a prescribed way through time. So we can capitalize on all of those different pieces of information to get information about time from a crystal. This is just a single quartz grain that you can see in cathodoluminescence imaging. But that really highlights all of these different pieces about time that I'm looking at, which is I'm going to be showing you information from crystal sizes using crystal size distributions, from melt inclusion shapes using melt inclusion faceting, and from compositional zoning using diffusion chronometry. Now, to get at many of these things, namely sizes and shapes, we need to have really precise measurements of those textures, of sizes and shapes. So we have been working hard to develop methods to do this in a robust way. And one of those methods uses X-ray micro-CT. So if you've ever had a CAT scan or seen a CAT scan, that's doing micro-CT. It's the same thing. So this is just a CT image of a brain. But we can do the same thing to a rock. So this is a piece of pumice in which we are kind of going through the z-axis. You can see all of that matrix melt, all of those vesicles, and you can see these bright things that are the crystals that are popping up. Now, to get a scan like this, we could go and do it on a medical CT scanner at the hospital, but that comes with trade-offs in terms of resolution. And so a lot of what we do is actually using a synchrotron. So this is where a lot of the work that we do is at the Argonne National Lab. You can see it's this big, huge circle. And inside of that circle are these little hutches. So what happens is there's a little ring inside in which electrons are accelerated. They're thrown out into this bigger ring. And then coming off of that ring at particular angles are these little hutches. And when that beam of electrons goes in, has to move into one of the change its direction, it loses energy. And that energy is in the wavelength of an X-ray. So you can get these beautiful X-rays coming into these hutches just by changing that angle of that beam a little bit. And so this is what it looks like in the beam line where I work. So the beam comes in here. We have my sample. You'll note that I'm studying a very small piece of pumice to study a very large super eruption. But what it is, it sits on this rotating chuck, and as you rotate it around, the X-rays go through it. It hits this scintillator, which converts the X-rays into visible light. That visible light hits a mirror, which then goes into the camera and captures an image. And we can change this setup in different ways to basically get different kinds of images, to get different kinds of maps. And so this is what we have been developing, these different ways of mapping rocks. One is using basically standard absorption X-ray tomography, which is just a grayscale map. If you've ever used an SEM and taken a backscattered electron image, it's basically giving you the same information in so much as things that have heavy elements in it, like iron, will be bright. So things like this, so magnetite, and things with lighter elements like sodium and potassium will come out in lighter shades of gray. We can also use something called differential absorption X-ray tomography, which is an elemental map. So what we do there is every element has what's called an absorption edge. And if we image the thing below and above the absorption edge and we subtract those two things, only the materials that contain that element will show up in our images. And so that's what we've done here. And so you can see these little titanite crystals that are colored pink. That's false color. But these are things that are highlighted in a cerium map because titanite contains a lot of cerium. And so then I can overlay that on top of my standard absorption map and get information about the distribution of these different minerals. And then finally, we have something called propagation phase contrast tomography. For those of you who are taking mineralogy right now, or have taken it recently, what we're basically doing here is enhancing the Becky line around objects. It's not exactly the Becky line, but you can think of it that way. And the reason we want to do that is because hopefully you can tell that these melt inclusions inside this crystal are very hard to discern from each other. And so if I tried to use grayscale filters to find them, the computer would not really be able to do that. So instead, what we do is we basically enhance the sample to detector distance. That's all I'm doing. I'm just changing the distance. And what that creates is it enhances the edges around objects. It enhances the Becky line-like thing around objects. And so that instead of using grayscale filters, I can use edge detection algorithms. And so I can find these things based on their edges and get information about them. So these are the three different kind of techniques that we've been using in our micro-CT. And when we do that, we can get all kinds of great information. So this is a piece of pumice in which I've taken out all the glass, but you can see these really nice twinned feldspar crystals sitting inside. And so you can tell that we can really get information about the distributions and the sizes of these things. These are a few quartz-hosted melt inclusions put back into the quartz grain, which is a nice hexagonal bipyramid that you can see as it's rotating around. So these images are really useful for getting excellent qualitative information, right? We can see things with our eyes that we can't see when we're just looking at our piece of pumice. But what we also want to do is get quantitative information out of them. So using, for starters, crystal size distributions, we can look at time. And so crystal size distributions are exactly what they sound like. On the x-axis, you have crystal size, and on the y-axis, you have population density, which you can think of as the number of crystals. And we get this from our standard and differential absorption X-ray tomography. And on a plot like this, you know that the slope of a line is going to be a function of crystal size, 1 over crystal size. Now, if the size of a crystal is a function of how fast it grows, its growth rate, and the time that it is sitting there, if you know something about the growth rate, or if you know something about the crystal size, you know something about the growth rate, and you know something about the slope, you can back out information about time. And so this little schematic here shows how the slope of a line on a crystal size distribution will change through time. It will become increasingly shallow. This is a common shape of a crystal size distribution. You can hopefully see that it has two portions. One is a shallow sloped section describing large crystals, and the other is a steep sloped section describing small crystals. And we can actually use these different parts of the crystal size distribution to tell us different time scales. So we can use this shallow slope section to talk about the phenocrysts, the crystals that are growing large and are sitting in the magma while it's sitting there and growing. And so we're going to use this to look at magma residence times, this longevity question. These smaller crystals are what we call microlites, so these tiny little things in here, these little dots, and they are typically growing during the eruption process itself. And so we can actually use these to look at questions related to how fast do these magmas ascend and erupt. But like I said, for this part, we're going to focus on the phenocrysts. So now I'm going to show you the results of the phenocryst size distributions for several of our super eruptions. So we have the Bishop Tuff, we have the Peach Spring Tuff, and we have the Arunui and the smaller volume topo eruption. And so these are coming from several different mineral phases, but what hopefully you can see is that their slopes are very, very similar. And what we get from this is that the residence times of these magmas are on the order of hundreds to thousands of years, so their slopes are somewhere in here. And this comparison that we can do between Arunui and Taupo shows us that the size of an eruption is not necessarily a function of time, of how long the magma is sitting there in the crust. There's something else that's going on that drives how big an eruption is going to be. So crystal size distribution says residence times on the order of hundreds to thousands of years. The other piece of information, or another piece of information we can get from our micro-CT, is looking at the shapes of melt inclusions. This is melt inclusion faceting. And the idea here is that a melt inclusion, when it's first entrapped, it's a sphere. And over time, through dissolution and reprecipitation of material in a different place, that melt inclusion will become increasingly faceted. And when something is fully faceted, it takes on the inverse shape of its crystal host. So what that means is if we take a quartz crystal is typically a hexagonal bipyramid. A faceted melt inclusion will look like a hexagonal bipyramid. And so here you can see this. I was very lucky to get this. This cross-section through a single quartz-hosted melt inclusion that has this hexagonal shape to it. But yes, so there's that. And so the way that we actually get information out of the micro-CT is we'll image our grain, and we'll get the shape of the melt inclusion itself. That's what's here in red. And we can overlay it with an ellipsoid of the same volume. So why the same volume? And the reason is because in this process, volume doesn't change. The volume stays the same. You're just redistributing material. And so this delta V here is the volume of material that's been moved in the faceting process. So we approximate the original shape of the melt inclusion with this ellipsoid of the same volume. And so that means any of the material that's sticking out of that ellipsoid is the volume that has moved in the faceting process, that it's moved from that originally rounded shape. We can take that delta V and put it into this scaling relationship, which is a function of predominantly the temperature and the diffusivity of silica in melt when we're looking at quartz, and we can back out information about time. And I'm going to just show you this plot because it's the one I'm going to show you the results on, but it can be a little bit complicated to understand. So here on the x-axis, we have the time that would be required to fully facet a melt inclusion. We can just calculate that. If we know its size, how long would it take to fully facet it? And then here is the time that's recorded by the actual shape of the melt inclusion. So when it's on this 1-to-1 line, that means that it is fully faceted. So when a melt inclusion first gets trapped in a crystal, it will sit here on the x-axis. And over time, it will move, as it facets, it moves up the y-axis until it hits this 1-to-1 line, at which point it can't do anything anymore. And so you'll never see a melt inclusion in here. But we can use information from this section to get our timescale information. And so now I'm going to show you some data from several different eruptions again. So here we have the time to the current shape is really what we care about here. And hopefully what you can see is that all of these melt inclusions in these 3 different super eruptions are giving timescales of about 500 years or less. The errors on this are about a factor of 1.5. But even when you include that, we're not talking about an order of magnitude change in the time here. And some of the eruptions out of New Zealand, they themselves are really on the order of 100 years or less. So very similar to what we were seeing with the crystal size distribution, melt inclusion faceting suggests residence times of hundreds to thousands of years. Now the final piece of timescale information we get is not from micro-CT, but instead it's using zoning inside of crystals. And zoning is a disequilibrium feature. Crystals do not like to be zoned, and so at high temperature, given enough time, diffusion will act to get rid of zoning. But if an eruption happens and it gets too cold for diffusion to really be moving, we capture this zoning in our crystals. And so we can use the existence of zoning right now to tell us something about how long that crystal spent at high temperature in the magma. And so if we take a profile perpendicular to a zone boundary, we might assume that originally the composition on this side is different from this, and that the boundary is a step function. It's a sharp boundary between them. And over time, diffusion will act to mellow out that boundary. And then it gets captured at the time that the eruption happens. And we can use the difference in the shape of our initial profile to the current profile to back out information about time, again using the diffusivity. In this case, I'm looking at the diffusivity of titanium and quartz. I'm using cathodoluminescence images to get this, not actually titanium maps. And the reason for that is displayed here. So hopefully what you can see is that this has much higher resolution and much better detail than this actual titanium map. This took 15 minutes to collect, and this took 4.5 hours to collect. So we can get a lot more data when we do that. But we do have to be very careful because you can see that some of this very fine scale oscillatory zoning doesn't show up in this map. And part of that might be a resolution problem, but part of it might also be that it's not actually titanium that is causing that zoning. So we have to be very careful about which zones we use for this problem. But when we do that for 3 of our eruptions, we can see yet again that diffusion chronometry suggests residence times of tens to thousands of years here. So very consistently, what we are seeing is that over and over and over, the crystals are giving something on the order of tens to a few thousand years. I haven't resolved any discrepancy here, right? I want to be very clear that there is no resolution in what I'm telling you. But these are kind of the conclusions from that. First is that multiple data suggests that this final period of residence is pretty short, on the order of decades to a few millennia. But we still have discrepancy in results from other methods. First, you can say, well, Ayla, most of what you did was based on quartz. How do you know that quartz was there the entire time? And that's a fair critique. And so we've done some sensitivity tests and found that quartz is probably underestimating these timescales by about a factor of 2 to 3. Still less than orders of magnitude, right? We're talking about orders of magnitude change here that we care about. But what I think, and what I think the community in general has come to a consensus on, is that this is not actually a discrepancy, that different mineral phases can record different parts of time in the system, and also different methods have different levels of resolution. So especially a major comparison that people use is zircon crystals, which are really robust. They hate to be dissolved. They can stick around for a really long time, versus quartz, which is kind of a diva. It just like not very robust. And as a function of that, you could be recording two very different things if zircon can go through a whole long history that quartz can't manage. So I think it's the integration of these different timescales, or of these different mineral phases and methods together, that is going to get us this really robust understanding of these magmatic systems, and that it's not so much of a discrepancy as we might think. And then I think it's very interesting to see that the residence time of these really supersized super eruptions versus these smaller volume eruptions is very similar, and suggests that maybe the size of an eruption is not a function of residence time. Alternatively, this is also telling us something about the geometry. If we have multiple smaller volume magma bodies that are simultaneously erupting, then perhaps we would expect them to give the same timescale. So if super eruptions are just multiple smaller volume eruptions, maybe that's not so surprising. Okay, so how long? Final residence time looks to be decades to millennia. So now let's look at why these things ultimately erupt. And there are two N-member models. One is that they're externally triggered. You have hot, gassy, mafic magmas coming into the system, adding volatiles, or you have some kind of intrusion or an earthquake that might destabilize something. The other is that they're internally triggered, that buoyancy-driven overpressurization of the system, this buoyant body coming up, crystallization of magmas that are fluid-saturated produces a lot of bubbles, and that could make it erupt. So there's these kind of two N members here. And I think that in the case of some systems, this external trigger seems to really fit the bill. So if we look at this Peach Spring system, where you might remember I told you that it goes from high silica rhyolite in the outflow out here to trachyte in the caldera. So we have this nice geochemical variation here. And we start to see really interesting things when we look at the crystal populations. So first, if we look at zircon here, I'm going to show you these plots of hafnium versus titanium, where titanium in zircon is a proxy for temperature. But generally what you would expect to see as a system is cooling and crystallizing, a simple cooling and crystallization history, is that the composition of a zircon will go from low hafnium to high hafnium and high titanium to low titanium, so down and to the right. And so what we're going to look at is the compositions from the cores, the earliest stuff to grow, versus the edges, the later stuff to grow. And so if we look at the cores of zircon crystals from all three of these different parts of the eruptive deposit, we see that they're pretty much sitting in the same location in hafnium and titanium space. Now, when we look at the edges of the high silica rhyolites in the outflow, the first material to erupt, we see that they do what we expect them to do. They go to lower titanium and higher hafnium. The next stuff to erupt, the low silica rhyolites, sit somewhere in between, and you guessed it, the last stuff out seems to show some kind of hotter temperatures and less evolved compositions, opposite of what we would expect for just simple cooling and crystallization. So let's keep that in mind. Now let's look at crystal size distribution. So here, and crystal textures in general. Here in the high silica rhyolites, we see these beautiful euhedral feldspars. And if we look at the feldspars within the caldera itself, in the trachytes, we see that they're all chewed up. And this is consistent with what we see in CT. So these are titanite crystals. You can see they're beautifully faceted. And here it's a total piece of Swiss cheese. No, not a happy titanite. And we see this being reflected in the crystal size distributions. This blue one is from the high silica rhyolites, follows that pattern that we expect to see in a size distribution, whereas in the intracaldera, we see this kind of backbending thing that is probably reflective of resorption, redissolving these crystals back into the system. Okay, so we have that. And then when we go out to the field and we make our field observations, we see these enclaves, these mafic enclaves with crenulated edges within the caldera itself. So putting all of these things together really suggests that there's this bit of heat that came into the system, probably from some mafic magma that's coming in there, warming the system up, but it hasn't touched the entire thing because the first stuff out didn't get touched by that heat pulse, and the last stuff out did. And so it might suggest that this was the triggering event that actually drove the system to erupt. But I want to put a little bit of a caveat on that in terms of when we're thinking about what the records are in terms of the compositions of these crystals. So here are a bunch of quartz crystals from a single eruption, and you can see that they have a lot of different textures in them. And one standout feature from some of them is that they have these really bright rims on them. And this has been well known to be something that you see in quartz fairly frequently. So this is a quartz crystal from the Bishop Tuff by Wark et al. In 2006. And here you can see the titanium contents in these different zones. So what they notice is that within the inner part, it has low titanium, and this bright in cathodoluminescence is high titanium. So what you see are these high titanium, bright cathodoluminescence rims that are enriched by about a factor of 1.5 to 2 relative to the cores. Also in these bright rims are high CO2 bearing melt inclusions. They're enriched in CO2 by a factor of about 2 to 4 relative to melt inclusions inside of the crystals. And so what's interesting is that titanium in quartz is associated with temperature, high temperature, and CO2 is associated with high pressure. So given these observations, you might say that these quartz crystals, similar to those zircon crystals, they were growing from some hotter, deeper, something at the very end of the lifetime of these crystals that was influxing with heat deeper in the system. But what's interesting is that there are some studies that suggest that crystal growth can produce disequilibrium concentrations of titanium in quartz. So what do I mean by this? Basically what you have, if this is the quartz crystal and this is the melt, you have an interplay of how fast the crystal grows versus how fast an element diffuses away from that growing boundary in the melt. And so if you grow faster than you diffuse, you can have a concentration gradient in the titanium here, such that your next increment of crystal growth would be sampling very high titanium, even though the melt in general is actually low titanium. And so this is not actually the equilibrium concentration that you would expect to see there. And so you'd have these bright rims on these quartz grains that aren't necessarily reflecting anything about temperature. And so you might be asking, well, what makes you think that that's even something that matters? And that's fair. And it's just that there's some evidence for late stage, really rapid growth of crystals associated with the eruptive process itself. When you're decompressing, you can grow faster than you would. And so that suggests that these high titanium rims may have grown much faster than the cores. And also you have those tiny crystals, those microlights, the ground mass that grew during eruptive decompression, and the timescales of that process seem to correspond with the timescales from diffusion chronometry. So anyway, suffice it to say, despite all those details, the point is that there is some evidence that you might be having disequilibrium growth and therefore faster growth than you can diffuse away. So the question is, can high titanium bright CL rims and high CO2 melt inclusions actually be due to fast growth rather than a change in temperature and pressure? And so we did some models, and you can see kind of what the end result of one of these are. So if this is the quartz melt boundary here is that gradient that you end up getting for a growth rate and a time, a specific one. And so this is saying how enriched would you be at that boundary between the crystal and the melt if you were to capture quartz then. And so then I do this for a bunch of time scales and a bunch of growth rates. And you can see that at growth rates of 10 to the minus 10 meters per second or faster, you can get the concentrations that we actually see in the crystals themselves. We can also do this for just if we think about how thick the actual rims are that we measure, we find that growth rates of 10 to the minus 9 or faster can actually get us what we see in the magmas. And so these growth rates, 10 to the minus 9 to 10 to the minus 8, are actually the growth rates that have been estimated for the growth of those microlights and for the growth rates of these really fast growing rims. And so what this really points out to us is that perhaps this idea that really fast growth during decompression, during eruption, could actually explain the rims and not a process that creates high temperature and high pressure. So I think the point here is that integrating these multiple data sets suggests that some eruptions are motivated by external perturbations, but you have to be really careful when you're interpreting a single data set, and that crystal records are complex, and they might record local processes rather than the global process of what's going on in the magma. And so not always is it necessarily indicative of this thermal recharge or perturbation of the system. And so maybe, for instance, in the Bishop Tuff, perhaps that was an internally triggered supereruption as compared to an externally triggered one. And there's some other evidence that suggests to that. And then finally, that there are these eruptive processes being recorded in both the crystal zoning and also the ground mass. I didn't talk about that in too much detail, but we've done some work looking at those. So putting that together, why do these systems erupt? In some cases, they look like they're internally triggered, in some cases, externally triggered. So to wrap all of that excessive amount of stuff up, if we come back to our original cartoon, this is where we get. We see that there's some restricted range in the mid to upper crust in which these magmas are being generated, and they can sit there as single bodies or multiple bodies. We see that the mush model and the flux model both have some application here, and that different eruptions might be created in different, these rhyolitic bodies might be created in different ways. We see that the final residence times of these magmas are decades to millennia, while the eruption themselves is on the order of days to weeks. And that external or internally triggering is a possible way. Both of those seem to have evidence in the rock record for creating these ultimate big eruptions. So that is my perspective on how you build a super eruption. And just to leave you with the Bishop Tuff and think about how much magma, 1,000 cubic kilometers of magma came out of that sucker and made a big hole in the ground. So they're pretty cool things, and everybody should study them. And with that, I'm happy to take questions.
Thank you, Ayla. We have some time for some question and answer. And Ayla, if you wouldn't mind repeating the question so that people at home can hear what folks are asking.
Sure.
Questions, please.
Yes.
So early on, when you were kind of introducing us to the 6 different kind of super eruption sites you were looking at, you mentioned that the quote-unquote, the not-so-super eruption of Taupo, if I'm
Yep.
saying that right, had a really constrained silica content. Why do you think that is?
So she asked, why would the Topo eruption have that really constrained chemical composition? Why is it only like 1 weight % silica variation? And Topo is really interesting, in part because it's extremely crystal poor. So very, very few crystals, on the order of like a weight % crystals, whereas these are all crystal poor rhyolites, but that one in particular is. And basically what I think is going on there is that the system was buffered at a composition. And so these systems are what we call eutectic systems or near invariant systems, and it means that their composition is very constrained. And that's actually a really awesome tool for us, because it actually allows us to use the silica content of that melt to get a pressure out of it, because if we know something about the thermodynamics and the equilibrium between those different crystals. And so what I think that is just saying is that it was at a particular pressure and its silica content was constrained there, and it had this particular phase assemblage, this particular mineral assemblage that was crystallizing there. Yep. Yes.
Ayla, beautiful talk. Thank you. I was really intrigued by some of the work you were doing on inclusion faceting.
Mm-hmm.
And at least my experience looking at things is, I think a lot about how do you even get an inclusion in the first place, because it's energetically unfavorable. And at least in my mind, I think about a pulse of rapid growth where you have a more skeletal growth of the crystal, then the growth slowed down and actually trap something. So in other words, I would think it would actually start out with a pretty irregular shape rather than sphere. And so I guess 2 questions related to that. One would be, have you looked at that in terms of these time scale calculations? And then also related to that, since it ties into your interpretation of those high titanium rims potentially being more a signal of growth rate rather than any sort of temperature change, do you also see
So, okay, so a few levels of things there. One is that melt inclusions often seem to actually be growing under disequilibrium growth situations, and so you might actually have a not spherical shape to begin with, right? So I'll start with that one. Yeah, so it's a really interesting question. How do you actually entrap a melt inclusion in a crystal? And in the case of, say, an olivine grain, you see a lot of evidence for skeletal growth in those. Quartz grains, not so much. We really don't see evidence of that kind of growth in the same way. And part of that is because you're temperature constrained in a different way than you are. So the undercooling that you have when you're crystallizing an olivine can be really large, whereas if you're at this invariant point, you're stuck there for quartz. So the process of that kind of growth doesn't seem to fit as well for quartz. That being said, I think it's still a really it's a question that I've long wished to better understand. But so by assuming the spherical shape initially, what we ultimately do is we maximize our time scale. Because if we're somewhere between a sphere and fully faceted, then we've just started out. It's like assuming that the diffusion profile is not a step function, right? By doing this, by assuming that step function, by assuming the sphere, we actually get the longest time we could get. Does that make sense? The other question was, sorry, can you repeat it?
Titanium in there and connecting that to the rapid growth and evidence for that, basically diffusion effect that you're talking about.
Yeah, so people have definitely looked at the evidence for boundary layers, right? So the question is, does the titanium in the melt inclusions give you any evidence of rapid growth too? Because in theory, if you're trapping them during that rapid growth period, you would be trapping higher titanium in there also. And so people have looked at the evidence for or against boundary layers, this boundary layer growth entrapment problem in melt inclusions, and have generally not really resolved anything. Now, people did that quite a long time ago with lower resolution methods, so it's something that we're thinking about coming back to. But the idea would be that smaller melt inclusions might trap that boundary layer, whereas larger melt inclusions wouldn't because they were larger and thus have a larger boundary, basically, so they might get that whole thing and homogenize it. And they don't see evidence of that boundary layer in the sizes of those things. So yeah, an open question, I think, but a very interesting point as well. Yes?
So in your Argonne National Labs setting, when you're collecting all that data and experiments, how much data do you generate, and what type of computer do you use to process all that data?
Yeah, when I started doing X-ray CT, it was, I don't know, I'm not going to date myself, but long ago. And the time that it would take us to generate a data set was the amount of time it would take us to carve a new cylinder of pumice and start to do our data. Data collection has gotten so rapid and so enormous now that it is becoming an interesting problem. So we use what's called monochromatic beam, and our data sets are somewhere from the synchrotron are somewhere on the order of 8 gigabytes. But if you use what's called pink beam, you end up getting like terabytes of data in 24 hours easy. We can do different things to make that data processing more achievable, but now a lot of our image processing computers have quite a bit of GPU on them to enable us to process things. Now, we have a micro CT in my lab at Stanford. It doesn't have the same kinds of capabilities that a synchrotron does. For instance, you can't tune the beam energy for differential absorption. So for that, for instance, for a zirconium map, I have to look at 17.9 keV versus 18.1 keV, like because the absorption edge is at 18.0. So I don't have that kind of control, but there's still a lot of micro CT that we can do on in-house systems that are not medical CTs. Those you can get up to like 25 gigabyte files pretty easily. So, so data storage, data processing, that is now has become the time barrier. So for Argonne, what you do is you put in a proposal and they give you beam time if your proposal is accepted. And you can do that 3 times a year. And usually you get 24, maybe 48 hours for a project like this. And so then you need basically the next 3 months to do all of that data processing. And even then it might be too long. Whereas in the past, like I said, when I started, we couldn't collect nearly as much data in a single session. and so like that time was enough to process it. But there's a lot on the image processing side to be done, as well as on the imaging side. How can we image better and how can we image process better, I think are very open questions that people are actively involved with right now. A lot of machine learning stuff for the image processing, not surprising.
Thank you.
Yep. Yes.
I have a question regarding your diffusion chronometry. How do you choose your transects that you measure and why do you choose them?
Yeah, it depends on the question that you're asking. So the question was, how do you decide what profile you're going to take in a crystal? So for instance, if I want to know something about this eruptive process itself, I'll usually pick an edge profile, because that is presumably what grew during the eruptive process or at the very end stage of this. But otherwise, I try to get into the cores. If I want to understand how long this magma was sitting there, then I need to know something from the center of my grains, right? Not always can you get right to the center, so it can be tricky. Those are also generally the most diffuse profiles. Not surprisingly, they've been there the longest, right? So it's partly a question of the resolution on your technique. So I'm using CL, photoluminescence, and that gives me really high spatial resolution. If you need to use something like an electron microprobe and get spots to actually sample the boundary, it differs in terms of what your question is and what you need to do. It also depends on what mineral you're looking at in terms of how anisotropic diffusion is. So in quartz, it's fairly isotropic, so I generally orient my grains along the C-axis. And that is also because I also get growth rates from my diffusion profiles, and I don't want to have an apparent thickness problem if it's like on the side, right? So, but in other kinds of minerals like olivine and plagioclase, there are anisotropies that you need to worry about, and so you need to orient very specifically for that. So it's, what can you go after? What is the question that I'm asking? Yeah.
Have you ever experimented with 3D metal printing? Because they have a lot of inclusions. Yet, that's their number one favorite.
3D metal printing? I haven't done anything with it. I mean, the tricky part for imaging those sorts of things is you can't get X-rays through them. So you can't actually image them that way.
There's a fellow from UCI, his name is Dr. Earthman. He's got a cool place.
Yeah.
I'm sorry.
That's okay. Let's continue this after. If you still have a question, come on up and chat with Ayla afterwards. But let's thank her one more time for an excellent talk.
Thank you.
Thanks for coming, everybody. We'll see you next Friday, huh? Mike, Eddie, next Friday. The last talk of the spring quarter. Thank you. Come on. Brilliant.
I hope people understand.
Yeah, you had the whole room. That was gorgeous.
Good.
Yeah.
Thank you.
You bet. There'll be a few Hannah students and others probably coming up to chat with you a little bit. And I'm just going to continue to talk to the folks at home. Thank you.
Good.
About 500 were watching you live.
500?
Yep.
What are people doing with their day?
Good question. Well, it's evening in the UK. That explains some of it, I guess. Okay, well, I appreciate everybody tuning in to this one. Let me swing the camera around here and say goodbye to everybody. So we've been at this a while. We've been doing this this Friday noon seminar thing where we're live streaming these talks on a regular basis. And so many of you have been so steady with your attendance, quote unquote. Whether you watch live in the middle of a work day or whether you watch this after the fact, it's just so terrific to have you with us. And this is a special treat to have Ayla Pamukcu up from Stanford to give her talk. And if you didn't catch the beginning of this is the Spirit Lake Pluton team, Ayla and Mike Eddy, working together on a series of volcanics and plutonic rocks exposed just to the north of Mount St. Helens itself. And so I'm continuing to entertain Ayla as well as Hannah Shamloo today and then tomorrow morning, and then Ayla is heading down to the field to camp with Mike Eddy and one of Mike's grad students and one of Ayla's grad students. And I'm part of the project, and so I'll be driving down, and I want to do at least one field video with this group of researchers, probably Sunday morning. Nothing live, but there'll be a field video coming, visiting with some of these folks as they bang on a few rocks and collect some samples in the Spirit Lake Pluton area. There's a few other field videos that have been filmed in the last few days that will be coming as well. Plus, the final of the 3 downtown lectures has been edited and be posting that, I guess, this weekend at some point. There's a lot going on. So, seems like we're still together, still have more than 350 of you watching. So I say thank you very much. I love you and goodbye from Ellensburg, Washington, USA. We'll see you next Friday for Michael Eddy's presentation entitled Hunting for Fossil Magma Reservoirs in the Geological Record. Enjoy the weekend. See you next week. Goodbye.